Right. Business analytics and data science is our topic. It's sort of intuitive, I believe, that whenever we build analytical models, and for the time being we will focus on models for predictions like trees or regression type of models, it's somewhat intuitive that we want and need to assess these somehow. And we have been examining some typical application for these techniques. You certainly remember the Schufa score, my credit scoring example, where we use classifiers to screen credit applicants, whether they are good or bad risks, and to then make money lending decisions according to such predictions. I would like to briefly discuss with you, when talking about model assessment, what are the criteria of an analytical model that you think are important to assess. What actually is it that we need to evaluate? Considering the type of models you know now, considering the type of applications you have seen, what are the things that need some proper assessment and why? What is the, or what determines, which factors determine the quality of an analytical model? How often the model predicted the right option? If we happen a model that recommends options to us, or maybe say actions to us, and provided we are in a position to judge in retrospect whether the recommendations were good, then that's something we probably can and probably want to assess. How often were the decision recommended by the model actually good decisions? So in credit risk, for example, how often did the model suggest us to lend the money, and out of these, how often turn these predictions out to be right? So we did lend money in the end, and then it was all repaid. That would be a right recommendation by the model. How often did that happen? So a follow-up question might be, well, 75% does not sound bad, but how good can we get? It's a good point. So this could signal that we might need some sort of a benchmark, which puts the 75% accuracy that you report into context. So in industry, we typically have this idea of a champion-challenger type of approach. Models are used in daily operations. The models that are actually used and deployed are the champions. And whenever you come up with a new idea, a revision of a model, that's going to be the challenger. And then you make this comparison. How does the challenger compare to the champion? And when it wins, it's going to be deployed and becomes the next challenger. That would be a way to address this issue. If we know that, let's say, out of 25% of all cases where our model provides some recommendations, these are wrong, we would want to do something about it. I think it also goes in your direction. Can we get better? You would not know a priori which recommendations are wrong. Where you be in a position to tell, right, then you could easily improve your model. But as you suggest, there might be ways to look at the confidence of a model when it makes recommendations. Maybe sometimes the model is just more confident that an action, lending money, is the right action to take, while in other cases the model is a bit more inclined to recommend not lending money, but it's really not sure. Maybe there is a way to diagnose such an element of confidence. By the way, this is the beauty of Bayesian statistics, where typically if you build models in a Bayesian manner, you get this quantification of uncertainty or model uncertainty for free. Sort of for free. If there is anything you get for free in Bayesian statistics, normally it's not so easy to do it, but it's integral to the Bayesian paradigm to quantify the uncertainty, and you make a good case why this is relevant. So you predict correctly 75% of all times. How does that add to the bottom line? Very typical question, very important, often hard to tell. It's really hard to tell to make this transition from predictive accuracy to business impact. Still, I think this is a very interesting area for research also, for us as, well, business-oriented people or business-oriented quants. It's a very interesting field of study, and there is clearly much to do. But we are currently sort of looking at very relevant bits, but we go very deep. We started off with measuring the, I call that the accuracy of model recommendations. How often are they correct? How often do they make sense? And from there on, you went deeper and deeper. Can we quantify the uncertainty to improve accuracy? Can we also capture the business impact of a model and its failures? That's perfectly fine. All these things are relevant, and we will actually focus on these bits. But there are also some other auxiliary points that matter in industry when we talk about the adequacy of analytical models. In this chapter, basically, I do want to focus on this element of predictive accuracy, very much the one you were jumping on straight away. Maybe you also had a look at the slides. There are further dimensions. We will very briefly look at them in the intro part. And then normally I leave these for read-up with regard to time. I do have some more content on these other dimensions of model performance. But let's first of all have a quick look at these. Just to revisit, we are within this analytical process where we pay attention to numerous tasks, data prep tasks, data transformation tasks, then actual modeling tasks. And although we haven't spent so much time on the modeling tasks so far, you can already grasp that in this process, we as analysts have to make numerous decisions. If you think about the data prep chapter, we looked into missing values. You need to make the decision whether you replace missing values or not. And provided you make the decision to replace missing values, not leaving them in your data, you need to decide how you replace them. Whether you use mean replacement, median replacement, whether you develop an imputation model, this decision is on you. Do you correct outliers through truncations? Or do you just leave them in your data? Your choice. You know that many algorithms exist to build models. Decision trees we looked at. You also know regression type techniques, and you have at least heard of all the fancy stuff, neural networks, tree-based ensembles, boosting, you name it. You need to decide which method to use in the end. And for each method, there are numerous other tweaks that you need to decide upon, how you basically handle these. So many, many decisions to make, and assessment is all about accountability. With most of these decisions, there is no theory to guide us, or little theory anyway. Experience will typically help us a lot, but then every problem is different from the previous problem somehow. The data science paradigm is very often based on empirical experimentation, or roughly speaking, trial and error. You are unsure whether you should replace missing values by putting in the mean or build an imputation model. Try out both options, run an analysis, which one gives better result, use that one. If there is no theory and no gut feeling, intuition, experience to guide you, do a test. And this is why you have to learn the programming bits in the tutorial, because this is how you make these tests. And if you are efficient, proficient with R, Python, or whatever is your language of choice, then you can make these tests easily and make these decisions in a sound manner and also in an accountable manner. And if somebody comes and questions your choices, You can say, look, I use a decision tree type of model because I run that analysis comparing it to regression, which we used to use in business, and I found I'm 10% better than the previous model. Okay, you're 10% better, that makes sense. So this is accountability. And that is the slide I was talking about. I'm trying to create this little or this little map here, landmark map, I don't know, where I just put bullets. The bullets are meant to depict dimensions, things worth assessing. These are drivers of model quality, if you wish. All of them matter. The first upper left one, accuracy, is the one that maybe matters the most for predictive model, but I put a bit maybe here. It's certainly relevant. We will emphasize it, but the other criteria also matter. Some are intuitive, scalability. If you are Amazon, you process these billions of transactions, you need a model that is scalable, that can digest all this data. That makes sense. If you have a model that governs the display advertisements that are showed at your web page, and the selection which ad to show is made instantaneously when a server accesses your page, you want to make the decision in a fraction of a millisecond to not delay the loading of the web page. So in certain applications, the speed with which a model produces recommendations matters tremendously. In some applications, credit screening, you can easily afford some seconds or more of runtime for the model to generate a prediction. That's totally okay. In a real-time setting, you must be a lot quicker. That's also an element of scalability. Is the model fast enough? When you build it, does that work? Can it digest all the data? But also when you apply it. Is it robust to changes in the environment? We screen customers for various other patterns. Customer behavior changes all the time. Is the model robust to changes in customer behavior? That's a more fuzzy type of dimension, but intuitively it does make sense. Robustness is good. If our model is robust, then we might not have to watch it all the time and can put our effort to different tasks. Then comprehensibility is a key thing in industry. Do we understand what the model is doing? And this is what your manager would definitely ask you about. So you make recommendations, and 75% of all cases, these recommendations turn out to be right empirically. Why is that? What's the model doing? How is the model coming up with these recommendations? How is the model determining that you are a good lender and you are not? At the not part, I'm trying to not look into anybody's eyes, so don't take it personally. But how is the model coming up with these recommendations? Do they make sense? Are they sound? You show me 75% accuracy, but is that robust? Will we see the same 75% if we put the model into production? This comprehensibility is really a mega topic, especially with novel machine learning type of algorithms that are set to be black box. And it is said that for them being black boxes that are not used or not ready for industry applications. I don't quite believe that's true. That's debatable. It's a sensitive topic. We will look at it. There are techniques to open the black box. But for now, it is enough to know that the ability to understand what a model is actually doing internally to some degree and how it is coming up with recommendations is of crucial importance, really, in practice. And this is what determines the fate of a model in practice. Even if you make 75% accuracy or you boost that to 85%, if people don't understand and you are unable to explain what your model is doing, it's not going to be deployed, I bet. Well, some application settings, maybe yes, but in most of them, people will just not trust your model. Many people have a hard time trusting math, and models are math after all. So just ready yourself for really explaining what your model is doing. So stick to that example, Schufa, banking industry, heavily regulated. Simple models dominate the industry. Understandable models that regulators know and that regulators will approve because they know these things. Now let's consider a different example, a hedge fund. It's all about money, really. I mean, to be fair, hedge fund people, they are really quants. They probably understand any model there is. But in settings where really the marginal accuracy improvement translates into millions of dollars easily, you might be willing to sacrifice some understanding, some understandability, some comprehensibility for higher accuracy. Clearly, comprehensibility is crucial. We will see very soon that there is often a little trade-off between comprehensibility and accuracy, and then it depends on the setting which one is more important or where we find a suitable balance between these extreme points. If you are not able to explain your model, how would you know that the 75% accuracy that you observe in your analysis is stable and will also be observed if we put this model into production? And this question of this argument is easier to counter if you really understand what the model is doing, and then can explain why you believe that the accuracy that you observe in your analysis is not something specific to your single analysis, but is something that is robust and has a good chance to translate into day-to-day operations. Because normally we cannot assess models in operation. That's okay, we do that. We monitor the models that we deploy that are run in production. Clearly we do that. That's model monitoring. But for an initial assessment of the model, to see whether it's better than the current champion, we do not use, or we do not have a production environment. We do that in the lab. And because of that, our analysis carried out in the laboratory might be a little bit over-optimistic. So maybe the 75% would translate into 68% in day-to-day operations. And, you know, this robustness, or call it stability if you wish, is also a matter of concern in industry, and this is one reason why people in general value comprehensibility. Okay, so take home, many things matter when you assess a predictive model. Accuracy is one, and now we are going deep, but there is more than accuracy. This is a typical exam type of questions. So this slide is important. You may want to put an exclamation mark or anything. When we talk about the evaluation of predictive accuracy, we have a predictive model, be it for regression or classification. We want to examine its predictive performance. We need two ingredients. We need a process which simulates a real-life application of the model. We will assess it in the lab. We won't assess it in day-to-day operations, but at least we want to simulate day-to-day operations. That's one bit. This will come down to organizing your data in a proper way. And in addition, we need a useful measure or indicator of predictive accuracy. How do we measure that? What is predictive accuracy? You said it's like how many times the model made the correct recommendation, which makes very good sense. For a hedge fund manager, it could be the degree to which a model is able to predict stock prices, closing prices, say, accurately to hit the closing price. For a marketing type of person, it could be the degree to which a model is able to predict customer spending volume. But how do we really measure that? So we also need an indicator. Process and indicator, these are the two ingredients that we need. And we'll start with the process perspective, where we essentially have three options. Well, actually we have two options or 2.5 options. There is the resubstitution estimates, which we should not consider an option in the scope of our course. And then the two options are split sample method and cross-validation. All these techniques suggest a way in which you can organize your data that you use for the whole modeling process. I focus on predictive models, and you will hopefully recognize this picture, one of my favorite pictures, another exclamation mark type of picture, right? Where we have a learning algorithm that we apply to some data to obtain a model, and where we can then apply the model to some other data and obtain forecasts for this other data. That's the slide in a nutshell. And the picture already depicts that we normally have two types of data, or not two types of data, but two data sets, where often there is a time delay. One data set we use to build the model. It's the one we apply our learning algorithm to. The other data set is the one to which we apply the developed model to produce forecasts. The resubstitution estimate is our first approach. It would basically suggest to use the very same data to build the model and to assess the model. And from now on, when saying assess, I mean to measure the predictive accuracy of the model. Model development and model assessment, you use exactly the same data. Hence, we call it the resubstitution estimate. And then noting that the performance of a model, the accuracy of a model that we observe in the resubstitution estimate is a function of its complexity, of its expressive power. The performance measure will typically be a function of the fit on the data, on the training data. Let's call it the training data. It's called the data we build the model from, the training data. And the fit of the training data is one ingredient to the performance measure, and its complexity is another. Just to compensate for the fact that more complex models have an advantage and have lower training error just because they are more complicated. And maybe you've seen these information criteria, AIC, BIC, different ways how to implement this functional F of training error and model complexity. You see these equations here that are based on the log likelihood, also something that will ring a bell, and then you also add the number of model parameters in one way or the other. And, well, the best model out of a set of candidate models would be the one with the smallest AIC or BIC. And I'm claiming here, don't use that. Resubstitution estimate should be avoided, and then the important bit, in predictive analytics. And that's maybe a bold statement. If you think about other teachings, if you think about regression analysis, you have done that in many courses, I bet. I've used tools for that, maybe you use Stata or R, SPSS, whatever. And these information criteria are omnipresent, I would say. I didn't put R-square here for a reason, but you could also think of the R-square. You can think of the Volt test of regression coefficient. All these things all these measures come from the very same data on which you build the regression function, on which you carry out your OLS. So I'm saying don't use that. This is a bold claim, and we need to understand why I'm making this recommendation here. Again, you've been trained to use these things. It's not that there are no good. Please don't interpret my suggestion in this way. It's not that there are no good. It's just, horses for courses. For us, that's not the perspective we need. And just that you've been trained to use these type of measures, and the scope in which you typically receive such training, lectures in econometrics, for instance, or statistics. Our purpose is often to build an explanatory model. I put the regression model here again. Very often the aim is to understand how the independent variables determine the target or the dependent variable, how x relates to y. That's something that we want to understand. Or maybe we have a hypothesis how a given x, let's say price, relates to a given y, let's say sales, and we want to test this hypothesis. We believe that the higher our price, the lower our sales. We want to test this hypothesis. We collect some data, we run a regression model, we look at the beta coefficient for price, should be negative. We then look at the volt test result, whether it's significant in the model. This way we can verify or reject our hypothesis. It's perfectly fine, and I call that an explanatory type of model. It explains the link between the independent variables and the dependent. And with regression, we can, once we have our model, once we know the betas, also use it to predict. We can just put in some values for x, we can put in some value for price, and let the model estimate a corresponding value for sales. That works. This is predictive modeling. Explanatory models facilitate prediction. Very often, however, there is this little trade-off that we can do better. Schufa uses logistic regression to construct their credit scores. They do all sorts of internal analysis, trying out other type of models. They could do better. They could be a bit more accurate by using a more powerful type of model. The paper by Schmüli and Kuppius is a very nice read, published in a top-tier journal, which makes this distinction among many other papers that also made this distinction. I like this paper, so citing it here. Useful read, have a look if you like. For some more details, why there is this trade-off, but I believe for us it's okay to note often we have this trade-off between simple interpretable models like linear regression and more complicated models in terms of predictive accuracy. The complicated stuff typically predicts a little more accurate. So for an explanatory model, the resubstitution estimate and all its instantiation like AIC, BIC, R-square, volt test, etc. make perfect sense. For a predictive model, the problem is that noting this trade-off between simple and more complicated models, we will also use more complicated type of models. And then, out of a sudden, these in-sample statistics make much less sense. You see here 3 examples of a classifier. One is a linear classifier. The leftmost one is a linear classifier. The task of the classifier is again to tell apart the red squares from the green dots by means of a line, and I have highlighted those observations where our model makes an error, where it does not recommend the right group membership or the right action. We see how a quadratic classifier shown in the middle makes less errors because to fit in the boundary between the two groups, the reds and the greens, more accurately. It's more powerful. It can fit a curve, not only a line. With this data and a linear classifier, there is an upper bound to the predictive accuracy I can achieve. With this curve, I can be a bit more accurate. Still, I can't be 100% right, or at least I can't be 100% right with a quadratic type of classifier. Whereas if I use a tree-type classifier and make the tree deep enough, I can easily fit this data without any error. And this picture is to show you any measure of predictive quality calculated from the training data is meaningless for a complex or expressive model like a decision tree, because it can always achieve perfection. R square of 1, no problem. Make your tree deep enough, there you go. It's easy, but it's meaningless. The point is not to memorize your training data. The point is to detect patterns in the training data that generalize to the population. Patterns among the population of borrowers that generalize to future credit applicants so that you can make good decisions on these applicants, these novel applicants. Hence, using the training data works only if your model is not too complicated. For regression, it's okay. For more complicated models, you should not use it. So let's look at the proper alternatives. That's the one, the split sample method. You take your data and you just split it. You have a training set and a test set. It's typically called the test set. Some call that the validation set. There's some ambiguity in the terms. I call it the test set. You build your model from the training data. This is where you run your OLS. This is where you grow your tree. Then you have your model, and then you let your model predict the cases in the test set, which is disjoint from the training set. And then you can carry out the comparison of predictions to actuals on the test set. So when putting all data here, maybe I need to point that out. Currently, I'm thinking about the development of a model. So all data means we have a table where we have x1, x2, xp, but also have y. We have information on the true label of an observation in our data. This is true for both the training and the test set, which is just obtained from the total sample that we have available. And hence, this assessment can then translate into comparing actual labels y to model predictions. So for the test set, we know the labels, that's key. And then we can compare the two. This is how to read that slide. And the splitting you can do randomly. Very often it's done randomly. Or if you have temporal data like stock prices, you would typically split the data sequentially, leaving, let's say, the last 2 months of data for testing. Well, as shown on the slide, so generally you have a ratio trained to test from 80 to 20 to 60 to 40, something in that region on average, as a rule of thumb. And the approach simulates a real-life application of the model in the sense that you apply the model to data it has not seen during estimation. The learning algorithm has never seen the test set. You have never used observations from the test set within your OLS or when growing your tree. And that's the key thing. This is how you can detect whether the model has only memorized the training data have identified some spurious patterns, fit some noise or artifacts that exist in the training data only, but fails to generalize to novel data, which is represented by the test data here. That's the good thing about the split sample method. You simulate a real-world application. And another good thing is it's simple. You see the slide, you see the picture, you know what's going on, so it's easy. Any disadvantage that worry you? And you have less data to train on. Absolutely. True. You could say, wow, but we have big data. No problem. We have enough. Maybe true. Sometimes still, you might not have much labeled data. Data is abundant, yeah, that's a given. But in predictive modeling, we need labeled data, and often the labeled cases are scarce, despite big data. And then this is costly. If we do the random sampling, we face sampling variation. So the estimate of performance will vary depending on which observations end up in the training and the test set respectively, and also on the ratio that we use to split the two. That's another issue, and these two are probably the main disadvantages. It's slightly wasteful in that we take out the test set, a larger fraction of the data, and never use that for model training, and sampling variation, which we could, however, get rid of by just repeating this exercise multiple times, doing the data partitioning multiple times with different random partitionings, finding the performance of a model on the test data, and then we can average the results. Here are some examples that you see. I'm depicting the variation in predictive performance. I measure that using accuracy. That's going to come later, don't worry. Higher values on the y-axis depict better performance. I use a toy data set related to credit risk that you can find online. A bunch of classification algorithms. Some you might know I have highlighted here, naive Bayes, logit, then the decision tree. And you see by looking at these box plots is how the performance that you observe varies a lot depending, it's only depending on your randomly sampled test set. Same size for these tests, training tests. The algorithms are configured in exactly the same manner. All the variation you observe comes only from having a different composition of the training and the test data. And you see how this is substantial. Looking only, let's look at the tree is a very good example, right? For the decision tree, so here we have something like, let's say this is 74%. Okay, maybe I'm a bit unfair by looking at the extreme points, but I already admitted that I exaggerate at times. And on the other extreme, we have like, that might be 57.5%. So we make classifications. We classify whether a credit applicant will pay back or will not pay back. And according to the decision tree, in one go of this split sample analysis, we find that the tree will predict the correct class label, good payer, bad payer, in 57.5% of all cases. And in another round, we find that it predicts the right label with 75% of all cases. I don't know how you feel, but to me it seems that 57 and 75 is quite far apart. So the sampling variation can be substantial, and this is the disadvantage of the split sample method. What do you think will determine how large the sampling variation is? I mean, the learning algorithm, that's clear because you see it on the slide. The learning algorithm will have an impact on how much variation you observe. We see that logit regression, for example, is less variable than the decision tree. What other factors will determine the magnitude of the sampling variation? It's important because it helps you to decide whether the method is your method, whether you should apply it or rather not. So if you really do have lots of data, the fact that split sampling is wasteful doesn't hurt you so much. And also the sampling variation that you observe is going to be a lot smaller than when you have little data. Like me here, I have 1,000 observations. That's not much at all. Okay, now, alternative cross-validation, the other approach, not too much different really. We again take all the data, and remember, when I put data here, that's x plus y, labeled data, and we organize it in buckets, typically 5 or 10 buckets that are disjoint. We can find these buckets randomly, and then we make one bucket our test set. In cross-validation, it's typically called the validation set, so I put val here. The red bucket is the one on which we test our model, where we produce forecasts and assess their accuracy. And the union of the other buckets, so in my example, 4 out of 5 buckets, we put together and train our model on that data. And we repeat that n times. 5, 10 are typical settings for cross-validation, but you can select a different number of iterations. And each iteration is basically equivalent to the split sampling method. It's just that we do the split sampling multiple times in an organized fashion, splitting the data only once into these buckets. And in the end, we can average the 5 estimates of predictive performance. Each validation bucket contributes 1 estimate of performance, P1, P2, P3, P4, P4, P5. We average over these, and this would be then our overall performance measure. We use all data for training at some point, so the model will see all the data across all iterations. That's a plus, no wastage. It's more costly. We run the model multiple times. That takes some time. This is the disadvantage. But our estimate of performance is typically more robust. That's a plus. That's cross-validation. There is a nice blog from which I took this picture. Maybe you like this picture better. I thought it's so nice you should really reference it. Split sample method, various n-fold cross-validation, but maybe let's just revisit the relative pros and cons. We did just talked about sample variation, and we can then clearly say that CV, I put the sign signal, so CV is better than I put SSM. Help me a little bit. What were the other criteria that we came up with to determine when to use which? Runtime we discussed, right? Runtime. Well, clearly SSM is better because we build the model only once, much less time. We talked about efficiency in terms of the use, making use of the available data. And there we said cross-validation again has an edge, because every data point that we have, every label that we collected, will be seen by our algorithm at some point. That's another plus here. Okay, I'll stop that here. These type of comparisons are something that matter to me, because when you go out, work in this space, it's the typical decision that you will need to make. How do I assess my models? And to make this decision in a good way, you need to understand the relative pros and cons of different options that you have. So you might want to think a little bit more about that and make sure you agree with these points, and maybe come up with some more pros and cons. There are some refined versions of cross-validation available. I leave these for read up. They don't change the overall paradigm in a substantial way, just more minor adjustments that can be used. And another useful perspective is that both split sample method and cross-validation simulate a real-life application of the model, and I count on you understanding how they achieve that. But they simulate only. It's not realistic an evaluation, and therefore it is probably overly optimistic. The performance of the model that you observe in a cross-validation exercise or a split sampling exercise is typically larger than what you will observe in production. And this slide tells us why. What is the bit where we only simulate the real production environment and where we simplify? What element are we missing in cross-validation or split sampling? The simulation is that we use data for assessment which the model has never seen during its development. The learning algorithm has never seen the test set. That's good. That simulates a real-life setting where new customers walk through the door and we screen these using our analytical models. However, the data we use in cross-validation is from the past. This is how we know the true labels, the outcome, the why. We know it because it's past data, and we take all this past data and then split it into training and test. In production, however, the model is applied to new data that originates later and dynamically. Customer behavior might evolve over time, and our model is then applied to unseen data that differs from the data that was gathered in the past and on which it has been trained. The distribution within the individual features might differ. The relationship between features might differ, and also the feature-to-target relationship might differ. That's a big problem in industry, especially in applications that are highly dynamic. If you do predictive maintenance and you want to classify based on sensor data whether some machinery needs maintenance, then arguably machinery behaves in a pretty controlled way. It's a machine after all. There are certain pieces in this machine that get worn out, get used, and at some point they will break. And by having some sensor measurements, we can imagine that we can predict this time where the machine will break relatively accurately and that everything will be relatively stable. Thinking about, as another example, financial markets or markets for cryptocurrencies, to put it to the extremes, everything is highly dynamic, patterns don't stay stable, things change, and the way to which today's prices relate to tomorrow's prices might be totally different tomorrow than it is from today. So we will need to update our models very often, and a cross-validation based assessment which uses only past data will be much over-optimistic because of these temporal changes. The environment and how the magnitude, to which it is dynamic, using some other statistical vehicle but my model. All right, let's have a look at the second bit. Accuracy measures. Well, that's a bit less fundamental. Here are some graphical examples again for regression and classification. The orange line always representing our models, and you intuitively see how the upper panel shows us linear models that fit the data a little less accurately than the lower panel, where we have more complicated models that fit our data a little better. You certainly know about residuals in linear regression, how they are measured as deviations from your regression line or your regression function, and you certainly know how, based upon these residuals, you can construct standard error measures like mean square error, root mean square error, mean absolute error, mean absolute percentage error, symmetric mean absolute percentage error, not shown here, and a couple of more measures. I don't talk much about regression analysis here because I believe these measures are familiar. And these examples already convey all you need to know. We clearly see how it always comes down to this comparison, actual versus estimate, which is instrumental in predictive accuracy evaluation. This is why we need label test data, otherwise we can't make this assessment. And whenever we have it, we have these forecasts and actuals produced on an out-of-sample set, a test set. We can construct arbitrary types of measures or just use standard measures like these. Same for classification. There are intuitive measures like the percentage correctly classified examples. Somehow the coloring was messed up here. Note the squares and the circles representing the two classes, which could be good or bad risk or something entirely different. We separate them by a line. The side where we find an example relative to the line determines the class prediction. It's either circle or square, and I have highlighted those cases that our line classifies incorrectly. And based on this analysis, we can work out the percentage correctly classified, or 1 minus that being the classification error, or we can look at the classification error, or PCC, within an individual group, so only among the squares and only among the circles. And this brings us to the standard type of evaluation of classifiers based on the confusion table or contingency table. We have class labels versus predicted class labels, so true labels or actual labels versus predicted labels. And for each class, we can either predict the true label correctly or incorrectly and end up with this 2x2 matrix, from which we can then again develop indicators, as we did in regression analysis with the mean square error and the MAPE. Here we have PCC, percentage correctly classified, classification error, and two other terms that you need to know, specificity and sensitivity, which are the class-specific accuracies. The specificity, for example, measures the ratio of correctly classified negative cases, or, well, bad risks in my case, over the total amount of bad risks. So how many of the bad guys do I classify correctly? And it's there is room for misunderstanding here. We have two classes, and they are generally referred to as positives and negatives. This is not meant to make some judgment. They are just labeled for the different classes. Specificity and sensitivity as indicators are based on this notion of positives and negatives. Sensitivity refers to the accuracy among the positives. Specificity refers to the accuracy among the negatives. In your application, what you define to be a positive or a negative is entirely up to you. So the meaning of specificity and sensitivity is not always well defined, or you can change the definition. But it's always a class-specific error rate. There are more indicators of that sort, but I would always associate them with the same family. I call these threshold metrics. Any metric, any indicator that comes from the confusion table, I consider a threshold metric. And the reason is that they are based on discrete predictions, where a model really issues classifications. Good guy, bad guy. That's not what models do. Most of them anyway, the vast majority. Typically what they do is they produce some sort of probability estimate, or at least a confidence, which is a number that is not a proper probability, But let's think about models producing probability forecasts, and then the comparison of actuals to predictions on the test set would really look like this bit here, where we have class labels that are discrete and predictions that are probabilities. And then we first of all need to translate the probabilities into class predictions by comparing them to a threshold, denoted by tau here on the slide. And only then are we ready to construct the confusion table, which in turn is a prerequisite to calculate something like a classification error. For classification error, we need the confusion table. For the confusion table, we need to carry out some thresholding. And this is why I call any metric that's based on the confusion table a threshold metric. And they depend on the cutoff. They are a function of your model and its predictive performance, yes, but they're also a function of the cutoff, which comes from you. It's another decision that you need to make. One of these many decisions that we talk about in the scope of this part, that you make. This is why you want to be a bit careful when comparing models in terms of these threshold metrics. The result of your comparison will depend on your cutoff. And this enforces you setting the cutoff in a meaningful way, which is not always trivial. And an entirely orthogonal type of analysis would be to just calculate the mean squared error between your binary class label or binary label of 0 and 1 and your probability forecast. The mean square error for probabilistic models has a special name. It's called the Breyer score, but it's just the mean square error. If you think about it, it's a bit odd, right? You just put your name onto something like a mean square error and say, this is my mean square error, this is the Breyer score. It happened long ago, so maybe. Anyway, the key point here is if we judge predictive performance by mean square error, there is no cutoff involved. So it's a different perspective toward accuracy. And this is, well, we don't have time to go into it in the detail that it would deserve, but this is really a fundamental difference. What a classification error measures compared to what a Breyer score measures. Here, for example, if I want to classify a bad risk, and let's say our label for bad risks is a 0, then a classifier that predicts a score of 20% for the 0 is better than a classifier that predicts a score of 35%, because 20% is closer to 0. And a classifier that predicts a score of 5% is even better, because it's even closer to 0. And this will matter when we calculate a mean square error or a Breyer score. The magnitude of the probability forecast matters in this calculation. Here, does it matter? No. All what matters is the score above or below the threshold. That matters. Nothing else matters. Oh, that's a good song, actually, in case you know that one. And this shows to us how different measures that are all legitimate, sensible, etc., assess very different aspects of a predictive model or a classification model in particular. A standard way, sort of compromise, is ROC analysis, receiver operating characteristics, curve analysis, where we generalize the confusion matrix and avoid its dependence on the cutoff by considering every possible cutoff. You find some characteristics here for a ROC curve. I leave that for you to read up. Let's look at the example. we start once more from the test data set with discrete binary class labels, actuals, and probability forecasts, and I'm showing you the resulting confusion tables that emerge from applying different cutoffs. And if we assume, and we may do so, that every analytical model delivers a probability forecast, the forecast will always be between 0 and 1, and thus every possible threshold can only be between 0 and 1. There is a finite number of thresholds. All we have to do is we try out every one of them, or maybe every candidate threshold from 1%, 2%, 3%, all the way up to 99%, 100%, and produce the resulting confusion table. I'm sketching that here. For 3 different cutoffs, and you can convince yourself that this is true, the numbers will work out, unless I have made a mistake, which is entirely impossible. Or with this slide, it actually is because I'm using it so many times. And if we have now n confusion tables, n being the number of cutoffs that we consider, we can create a graph where we take from each individual confusion table the class-specific accuracy, the sensitivity, and the specificity. Here's the graph. Just orientate yourself in the picture. Test set results, upper right part, different cutoffs and the confusion matrices. And you see how they look like. And then the ROC curve actually is a function of the sensitivity and 1 minus the specificity. Sensitivity, the fraction of positives that are correctly classified as positives. Specificity, fraction of negatives that are correctly classified as negatives, 1 minus that, so the error that we make among the actually negative cases. And we will always visit the point where we classify all cases as either positive or negative, which are the points 0, 0 and 1, 1 in ROC space. We are bound to visit these places. Every ROC curve goes through these 2 points. And then depending on our classifier, we have some shape like this here. And what's important to note is where we find the sweet spot, which is this one here. I wanted to use red. That's the sweet spot. Right? This is where you want to be. Make sure you verify, convince yourself that this is the sweet spot. Sensitivity equal to 1. All positives classified correctly. That makes sense. That's good. Nice. On the x-axis, we have 0, 0, 0, 0. 1 minus specificity equal to 0. So specificity equal to 1. Specificity being the fraction of correctly classified negatives are 1, so no error among the negatives. That's the sweet spot. And then we have our ROC curve, which considers all possible thresholds, and because of that, avoids the dependence on the classification cutoff that we face when using a single confusion table. We can then compare classifiers conveniently by looking at the ROC curves and judging which one is closer to the sweet spot. In this example, the blue one is always above the red one. It's always higher up north or northwest. This is where you want to be. And what is also done very often, especially if you compare many classifiers, and the graph would get a bit clumpy or overcrowded, then you can work out the area underneath the curve. That's known as the AUC, area under the curve of a classifier, and it's a single number summary of model performance, and it captures how far, how close to the sweet spot a model is on average. That's convenient to compare many classifiers in a single number. It also has a statistical interpretation and is related to the use statistic, which you can read up a bit more in Tom Fawcett's very nice paper, Introduction to Rock Analysis, published in 2006. And this is an indicator that you really want to know. We will use it a lot. It's like one of the best type of indicators, unless you have something better. And by something better, I would typically think of something that is really geared toward the business. You can show that for many measures that approximate business performance, the AUC is a reasonably good approximation to these measures, or at least it's related to these. And we will elaborate that in much more detail when we come to concrete business applications. So this is a very meaningful indicator, and we're going to use it a lot. So make sure you go through the slides and familiarize yourself. There are some alternatives here, some debate. Is it a good measure? Is it not? David Hand says you shouldn't use it. You should use the H measure, which is David Hand's measure, Hand's H measure. That has some nice statistical properties indeed. Other colleagues from London say, wow, well, you know, AUC is not too bad. I also did some empirical analysis. You can have a look at this paper, where we basically come to the conclusion that, you know, empirically, the difference between AUC and those more fancy measures like the H measure is not so big. So to sum up, AUC is one of the measures that you definitely want to have on your list to use in practice, to use in the tutorial, and to know about in the course and whatever, you know, comes with the course. Key part is really, how do we organize data to compare predictions to actuals, and what measures can we use to summarize the outcome of a prediction to actuals comparison. That's the key thing of this chapter, and I thank you for your attention and wish you lots of fun in the tutorial. Thank you.